viewpoint that we had before. So here's the outline of my talk. So I'll review universality and the unitary limit. Maybe Bira already covered this on Monday. And then I'll briefly discuss Schrödinger symmetry, which is an extended symmetry of non-relativistic systems that has some additional symmetries, which actually is quite useful to apply to multi-neutron systems. And then I'll apply this to nuclear reactions with neutrons and also discuss some data that Miki-san has already showed on Tuesday. And then if you're interested and if there is time, I can also talk about some applications in hadron systems, but it's a little bit off topic for this workshop, so it's not included in the main part of the talk. If you want to read up some of the details, there are a few references. So this is based on some work with Damson and also with Matthias Goebel, Daniel Phillips, and a forthcoming paper where some of the results that I have in this talk will appear. So let me remind you of the concept of universality. So universality means, in physics at least, that physical systems with very different short distance physics can show identical behavior at large distances. This term comes from the physics of condensed matter systems near a critical point, and here is some example. So here on the left side you see the phase diagram of a liquid gas system. So down here you have the gas phase, up here you have a liquid phase. They're separated by a first order phase transition that ends in a critical point where the phase transition is second order, and if you go around that critical point you can have a continuous transition from the liquid to the gas phase. So in this region, the distinction is not even well defined. Now, if, for example, you look at the pressure, at the density in the liquid and gas phase relative to the phase at the critical point, this follows a power law. So that power law applies in that small region around the critical point with some exponent beta. And now, if you take a very different system governed by different interactions, so here the example is a ferromagnet with one axis of magnetization. Again, you have two phases, positive and negative spontaneous magnetization, and you have a first order phase transition line. There is a critical point. And if you look at the magnetization as a function of temperature, this in the vicinity of the corresponding critical point here, it's also governed by a power law, and the exponent is the same. So that, at first sight, is surprising, since the microphysics of these systems is very different. But I mean, as you all know, in the vicinity of such a critical point, all that matters are the symmetries of the system and the dimensions, and that's very similar in those systems. They're in the same universality class, and therefore they have the same critical exponent. And at this critical point, the system is scale invariant. You have infinitely long thermal fluctuations, and you have scale invariance and often also conformal invariance. So this same concept I now want to apply to multi-neutron systems. So there will also be a critical point. There will be something that is analog to this critical exponents, and this will help to understand the behavior of multi-neutron systems. So in that case, the analog of the critical point is the so-called unitary limit. So that is a hypothetical limit, of course. No real physical system can exist in that limit, but nevertheless, it's very useful for theoretical descriptions and for understanding what's going on in physical systems. If you want to have a picture of how you could reach that limit, you can think of some potential as a fundamental interaction. So take a square well, for example, that has one bound state close to threshold, and now you take the range of this interaction to 0, and the strength is adjusted in such a way that this bound state ends up directly at threshold. So then that would be a way to realize this unitary limit theoretically. So in the real world, of course, as you know, you can have infinite scattering length. You cannot have zero range. All interactions have some kind of finite range. So this is a starting point for a theoretical description. Also, if you are in this limit and you have a bound state, then this bound state is in a highly quantum mechanical regime, because most of the time the system actually spends outside of the range of the interaction. So there is no classical analog for such a system. If you take this limit, then look at the two-body scattering amplitude, then so you take the scattering length to infinity, the range of the interaction, and in particular also the effective range to 0. So all these terms here in the effective range expansion will vanish, and the scattering amplitude is just I over k. So this is just, it's the maximum scattering that is allowed by unitarity, and this is where the name unitarity limit or unitary limit comes from. So this is a concept that has been applied in a variety of contexts. So in physics of ultra-cold atoms with this BEC-BCS crossover transition. So here that's a finite density system, and the unitary limit exactly connects these two regimes. It is relevant to the description of light nuclei with some extensions. And it's also relevant for neutron matter, and neutron matter is kind of what I want to address here today. So in order to get closer to my goal, we can first notice that the system at the critical point also has a non-relativistic conformal symmetry. Sometimes this is also called Schrödinger symmetry, because it's the symmetry group of the free Schrödinger equation without any interactions. So that was first mentioned in this context by Means, Stewart, and Weiss, and Son and Nishida. They really exploited that symmetry to describe many interesting aspects of these systems of spin 1/2 fermions. And now I want to apply this to neutrons. Neutrons are not in the unitary limit, but they're pretty close. So as we've heard many times, the scattering length is of the order of 20 Fermi. The range of the interaction is 3 Fermi. So as long as you look at energies that are in between the energy scales set by the scattering length and the effective range, so approximately 0.1 MeV and 5 MeV, then the system will be approximately conformal. And of course, if you get close to these limits, you could try to include corrections perturbatively, or the effect of the scattering length is relatively straightforward to compute if you just do pi-inverse EFT. So for the purpose of my talk, the results I'll show will be exact in the approximation that you take this large number to infinity and this small number to 0, but you can improve upon that, and even in the case that they're not exactly 0 and infinity, they're a good starting point for a theoretical description. So let me just briefly review what this Schrödinger symmetry means. So it's the standard symmetry transformations of a non-relativistic system, Galilei symmetry. So you have space and time translations, rotations, Galilei boosts. But then there are two additional symmetry transformations that are not usually a symmetry. One is the scale transformation. So you rescale space and time by a certain factor. It's non-relativistic. This is why this power of 2 appears here. And if you do that transformation, your fields will also transform in a very particular way with this control parameter lambda and some anomalous dimension delta, and this will be the analog of the critical exponent, as we'll see. And then in addition, there is a so-called special conformal transformation where x and t are transformed in a way that conserves all the angles in the xt plane, so this is why it's called conformal. So in that case, there are 12 parameters, and the generators of this group, you have Hamiltonian, total momentum, angular momentum, generator of the Galilei boost. So this is what you usually have, but then there is a generator of dilatations, this symmetry, and this special conformal symmetry. So you want to look at that from a renormalization group perspective. That is actually quite useful to understand what's behind all that. So let's look at a system of spin 1/2 fermions with zero range interactions. So that's an approximation to neutrons. And then, so you just have a contact interaction, and the contact interaction is fixed to reproduce the scattering length, which in this case is tuned to the unitary limit, and of course it's zero range, so all the other terms vanish. If you look at the system and do a renormalization group analysis for this coupling constant that determines this interaction, you find that there are two fixed points, and from the fixed points you can start to analyze this system. There is, of course, one fixed point is when G2 is equal to 0, then the right-hand side is 0, the coupling doesn't run anymore. And that just corresponds to the free case. So this is this free fixed point that you always have for a non-interacting system. That's trivial. But there is another 0 on the right-hand side. So this can also be 0 if G2 tilde is -1. And G2 tilde is the coupling constant with some factors absorbed to make the equation look simple. You can convince yourself that this value of the coupling exactly corresponds to the unitary limit. So there you have conformal Schrödinger symmetry. Of course, in the free case you also have it, but there it's more or less trivial. So there are two regimes where you have a conformal theory that is an approximation to the real world. And neutrons, so since these numbers are, let's say, close to 1/a equals 0 and RE equals 0, they're close to the unitary limit, so the neutrons are approximately conformal, and that is the basis for what I want to say about the properties of multi-neutron systems. So then, why is that symmetry useful? So the more symmetry transformations you have to satisfy, of course, the more constraints you have on the Green's functions of your theory. And so if you have a field that is a field operator in this conformal field theory, let's call it U. So in the real world, this will be a field that describes a multi-neutron state. So if you have 2 neutrons, 3 neutrons, 4 neutrons, this will be described in that limit by a conformal field like that. And here, this is the propagator of this multi-neutron system. So it's the propagator of an interacting multi-neutron state. And that's kind of the theoretical quantity that determines the things that are also measured in experiments. And the symmetry is so tight that this is determined up to one overall constant, the functional form, and of course also this anomalous dimension delta, our critical exponent, appears in that expression. And so it's more useful for our purposes to have the propagator in momentum space. So Fourier transform gives you this. And so there are some prefactors, there's some gamma function, but here this is where you have the dependence on energy and momentum, and you see that if delta is 3/2, then this is just 1/p² divided by 2m minus omega, so that's just your standard Schrödinger propagator. But if delta is larger than 3/2, you will have a function that has a cut and some that describes the multi-neutron continuum. And from general unitarity arguments, you can convince yourself that delta has to be larger or equal to 3/2, so it cannot be smaller. So the propagation of this multi-neutron system in that limit is very constrained, and we can use this to make some statements about its properties. So first you can take the imaginary part, then of course if you have delta equal 3/2, the standard propagator, you just get a delta function. But if delta is larger than 3/2, you get a power law function like that. So the imaginary part, of course, happens when this system can be on the mass shell. So that's what the theta function does, and then you have this power law. And so this is not a pole, but if you think in terms of singularities in the complex plane, but it corresponds to a cut. And this is where this name unparticle or unnucleus comes from, because it doesn't behave like a particle, which would correspond to a pole, but it has a cut. But of course, in this context, that's nothing particularly unexpected, because this U will describe a system of many neutrons, and if you have 2 or more neutrons, then of course the energy momentum relation is not fixed, and you just get the standard cut. And so then in order to make statements about the behavior, of course you need to know what this exponent delta is. So for free fields, if you have like a composite system of n neutrons, it's just n times the dimension of one field. But if it's interacting, it's not so simple to say what this delta is. Then you have to work a bit harder to calculate it. It's also, I talked about the fact that this is the approximation that you can calculate corrections to. So the corrections from finite A and finite I0 have been calculated by Damson and collaborators, and so you get perturbative corrections in 1/A and in R0. And interestingly, you see that the effective range corrections in linear order vanish. So the theory is actually a bit more accurate than you would expect. In the range corrections, at least the linear ones are suppressed. So then I said you need to know delta. So how can you get that? So you can do this in a field theory calculation, like the same way you calculate critical exponents if you're interested in critical phenomena. But there is another way which relies on a principle that's called operator state correspondence, that is very specific to this conformal field theories. And so you can actually calculate the anomalous dimension of an operator, a primary operator, so that's the operator that creates the multi-neutron state, by looking at the energy of that same state in a harmonic trap. So this means if you have a no-core shell model and you can solve particles in an oscillator potential, you can calculate these anomalous dimensions. And here, here I show the operators is the number of neutrons, the spin, and the angular momentum. And then now we have 2 anomalous dimensions if you want. So one, this delta free is what corresponds to the free fixed point. So in the end, this will just be the standard phase space behavior that you all know. So but you can kind of package the phase space behavior in the same theoretical framework. And if you are close to the unitary limit, these are the anomalous dimensions that you get. So for up to 3 particles, you can get them to arbitrary position. If you have 4 or more, then it becomes a bit more complicated. So the interesting fact is that there is a connection between this delta and particles in a trap, and therefore also between the properties of multi-neutron systems and spin 1/2 fermions in a trap. And for these anomalous dimensions, so I recently learned that predictions are available for up to 70 particles. So the symmetry prediction you can in principle make for up to 70 neutrons. And these, so the lower numbers here, they come indeed from no-core shell model calculations, but the ones for the large particle numbers, they're actually from David Kaplan's group at the INT, and they come from lattice calculations. What does this have to do with the nuclear reactions and a neutron energy distribution? So this is the application to that reaction. Think of a high energy nuclear reaction where a multi-neutron state is created. So say we have two nuclei, and here they called A1, A2, they come in, and then they will be a recoil particle in the reaction and any number of neutrons. And the energy balance is, so there is the difference in the masses, and then you have the kinetic energies of the incoming particles and the outgoing particles. And now the assumption is this a hard reaction, so when the energy scale of this primary reaction where you create the multi-neutron system is much larger than the energy of the neutrons in their center of mass. So imagine have a high energy reaction, the particles come in with high energies, the neutrons as a whole, the multi-neutron system goes out with a large center of mass energy, with a large velocity, and this recoil particle goes out with a large velocity, but in their center of mass, the neutrons are at low energy. So that's the assumption here. Then you can argue that the neutrons should come from a point, because if you look at the wave packets of the neutrons, so if it's a large momentum, you can argue that they must come from a very small spatial region. And then you can make this factorization approximation for the cross-section. So there is a matrix element for the primary reaction times the propagator of this multi-neutron state, and then so that you have for the matrix element, and then if you want the cross-section, you can use the optical theorem, and so you integrate over the momenta of the neutrons, and this gives you the imaginary part of this propagator of the multi-neutron system. So this is how delta comes into the game, by using the optical theorem. At the moment, this factorization is an assumption, but Daniel and some collaborators and I were working actually on a proof that also specifies the corrections to that approximation. And so if you have two neutrons, of course, it just reproduces the standard Watson-Migdal treatment. So how can you use this? Let's say you do an experiment. So there are two ways to do the experiment, at least. You can detect the recoil particle. So if you do that, then you have to look at the spectrum close to the maximum energy of the recoil particle. This is when the neutrons have low energy in their center of mass. And the cross-section will behave as a power law determined by this anomalous dimension. Or if you can detect all final state particles, in particular the neutrons, then you can look at the energy distribution of the neutrons in their center of mass. So for the two neutron case, again, what happens you can understand just looking at the dimer propagator in pionless EFT, because there you can have an analytical expression. So this essentially is this propagator up to some overall constants. If you take the imaginary part, you get this. And then you see if the energy of the neutrons here in their center of mass is very small compared to the energy scale set by the scattering length, you can neglect the ENN in the denominator, and you just get energy spectrum that grows with square root of E. So this is rising. It's at very, very low energy. And then if you are in this unitary limit window, so the energy is large compared to 1/ma squared, or a squared is infinite. Then you can throw out this term, and then it goes like 1/square root of E. So then it goes down. And that, so you want to look at more detailed studies of this two nucleon case. I also recommend this paper by Matthias Goebel and collaborators. So this contains calculations for this neutron-neutron scattering length experiment. in this knockout reaction of helium-6. So Carlos was also involved in that work. But the more interesting case, of course, is if you go to more neutrons. So there is a plot here. So what you can say without doing any calculation on any solution of Fadeev or Fadeev-Jakubowski equations is that at very, very low energies, if you look at the energy distribution of the neutrons in their center of mass, then for 2 neutrons, it grows with the power 1/2, then it falls with the power 1/2. So there you will definitely have a peak. If it grows and goes down, there must be a peak in between. But for all other cases, so for 3 neutrons, it grows with some exponent and then it grows with another exponent. And in between, of course, there will be a transition from one behavior to the other that conformal symmetry cannot predict, but pineless EFT can. And for 4 neutrons, it's the same at very, very low energies, 5.5. So this is really very, very low because here I have the energy in units of the neutron virtual state energy. That's 0.1 MeV. So this is a tiny window in a real experiment, and what's really relevant is this region. But it grows differently. For 4 neutrons, it grows differently. And I don't have the curve here, but Miki-san was asking for a prediction for the n equals 6 case, and that's the prediction. So for in the energy region, let's say between 0.1 and 5 MeV roughly, it should behave like e to the power 6.2. The overall constant, the normalization, is not determined by the symmetry, but the energy dependence is. And that, so this is something that you can check. And in the remainder of the time, I will actually also compare this prediction for 3 neutrons with your data. So before we want to look at data, we also checked this with theoretical calculations, because any calculation, if this is a universal property, any calculation should satisfy it. And so there we got this calculation of muon capture and pion capture on the triton, which produces 3 neutrons by Jacek Golak et al. So this was AV18 and the Urbana 9 3-body force, a realistic nuclear interaction. And you can see, so they did calculations with and without final state interactions. And at low energies, the calculations without final state interactions follow the free exponent, whereas the calculations with final state interactions follow very nicely the unitary limit exponent. So in the calculations, not very surprisingly, this is satisfied. Then, so we did this is not published yet, but it will be written up pretty soon. We also did a calculation in pineless EFT. So the pineless EFT calculation will also have the 1/A effects. This is by Tim Backert, Sebastian Dietz, Sebastian König, Damson, and myself. And so here, the P wave is the dominant contribution here, and the green line is the calculation, and you see that the asymptotics satisfy the prediction from conformal field theory, but now you also have the curves that interpolate in between. And so here is a comparison of the SP and D wave contribution. So it is SP and D waves between the dimer and the third particle. And you see that so the source has the same strength for all these contributions, and the P wave dominates. So this is what we can compare to Miki-san's data, which he kindly sent to me. So these are the most low energy data for this. So that's not a hard reaction now. It's a charge exchange reaction. But still, in this case, the triton source, so these are the data points for 2 different momentum transfers. And the red line, red dash dotted line, this is just the conformal exponent, whereas the blue line is pineless EFT. And both are consistent with the data. So for this system, this point-like approximation, that the structure of the initial state shouldn't matter. This is well satisfied in this low energy region. And there is no structure, also no peak. So there, and so if we compare to this older experimental data for pion capture, this is also consistent. So then, if we talk about 4 neutrons, then, so this is the plot that has been shown several times. So, I mean, this goes up in energy up to 60 MeV. What I've been talking about only applies in this very low energy region. So this peak here is outside of what I can discuss. But so here, now there is a clear peak, but as I argued before, this is a kind of a sketch of what this should look like. Very, very low energy, 0.1 MeV, so that you can't see in this plot, so it's essentially irrelevant. You would just see this power law here. And there is no peak. So, I mean, if you just have the standard neutron-neutron interactions, for neutrons produced in a point, there is no peak. And so this calculation also includes the di-neutron correlations in the continuum, and they are as strong as they can be because it's in the unitary limit. So, so then you can ask, where does this peak come from? And sort of, I think the most likely hypothesis at the moment is that it's a structure that remains from the initial state, and Rimas and Emiko and collaborators, they did a calculation where they exactly showed that if you include a wave function for helium-8, that at least the neutron wave function, that you can get a peak like that. So what we did also very recently here, this is just the conformal field theory description. Then Tim Buckert, so he's a student who was here last week for the summer or I guess it's more like a winter school here. So he did a pineless EFT calculation of this 4 neutron spectrum. So this is preliminary, doesn't have very many points, so this is why it's wiggling a little bit. And the calculation in pineless EFT is this blue line here. And he also plotted the contributions from the 2+2 channel and 3+1 channel in this Fadeev-Jakubowski decomposition. So also here, the main contribution comes from the di-neutron channel, and it agrees with the conformal prediction. And there is no peak. So if you don't have any structure from that is imprinted from the initial state, then there won't be any peak in the spectrum. And so that very different calculations show that. So on the other hand, for the triton case, the 3 neutron case that Miki-san showed, there was no imprint of the initial state, but it also was a very different nucleus. So the triton maybe is less clustered than helium-8 is. So that understanding that better is, for me, one of the key questions. One thing, so I'll just show this briefly because Daniel might have shown this plot for a core knockout of 2 neutron halo nuclei. We also did a study with Matthias Goebel and Daniel, where we looked at the neutron distribution for different nuclei, and there we also didn't find for the shape of the distribution any dependence on the initial state. So that strong dependence seems to be a specialty of this helium-8 reaction, as far as I can say. So since I'm already over time, let me summarize. So I introduced the method of universality in strongly interacting quantum systems, and try to convince you that from this approximate conformal symmetry you can make some very general statements also about multi-neutron systems. Let's see. And so for me, it's important to understand the difference between 3n and 4n and the initial state dependence. And there are some other applications. As I said, you can talk about charm mesons or possible applications in ultra-cold atoms where maybe this limit is realized even more precisely, and the extension to systems with the Efimov effect also is interesting, but then you don't have the conformal symmetry anymore. So thank you for your attention.
Thank you very much for this very nice presentation. We have 3 minutes left for quick questions, but remember there is always a discussion time. So.
Hans, thank you for this nice presentation. Just very naive question. I think you said, but just to see if I got the correct understanding. So this has to do with the short distance behavior of the wave function when you go to the unitary limit, is that? So you mentioned about a trap, I mean harmonic oscillator, is that? It's just the short range distance behavior
I would say
of the wave.
it's a property of the long range.
Long
or
range. Okay, so I still have to understand. Okay.
So this issue with the trap, this is, I mean, you're referring to why you can get this delta from the, so that is something. So it has to do with the fact that the only potential that also has a quadratic dependence on the same dependence on the distance as the kinetic energy operator is a harmonic potential. And if you look at this is also not my work. So you can if you look in the papers by Son, but the generator of the special conformal symmetry transformation that actually has also this x squared operator in. And because the generator of the special conformal symmetry has the same dependence of on position as the harmonic potential, you can make that relation between the energy in the harmonic potential and the anomalous dimension. So that is a useful coincidence. But if you didn't have that, I mean, you can still calculate this anomalous dimension using other methods. And for the three-body system, I mean, you know how to do it by solving this transcendental equation and calculating this S parameter. It's also known from Efimov physics and so on. So this S is related to the anomalous dimension just by a constant shift. So.
More questions? Yes. Yeah. Okay. There is another one here.
Hans, you, at the very end, you mentioned possible application to Efimov physics. But I mean, in the systems that you are looking at, the scale invariance and the full conformal group is broken by explicitly by small corrections, right? As you know, in the case of Efimov physics, it's an anomalous breaking of scale invariance right from leading order. So what's the hope that any of this can help understanding?
Yeah, so that's a very good point. So I mean, in the systems with the Efimov effect, you don't have even conformal symmetry as a starting point, as you rightly say, it's broken from the start, but it is not broken fully, right? So there is this remnant discrete scale invariance, as you know, and so the hope is that, I mean, so everything that relies on the conformal symmetry, you can't translate to that case. That's clear because the symmetry is not there. But there is a hope that you can translate some of the concepts and also make certain predictions about the behavior of the endpoint function. And there is one paper by Sergei Moros, and so this is about the 1/r² potential. And as you know, the 1/r² potential is equivalent to the three-body system in the unitary limit. And he, not by using symmetry methods, but by explicit solution, because in that case, I mean, if you're good with special functions, you can do that. He constructs the propagator that is analog to this multi-neutron system propagator, and he shows that you can define a concept of anomalous dimensions that is not the same as in the conformal symmetry case, but has something similarities. And so the analog, I mean, so the naive analog is that if you think of the three-body system and this transcendental equation that you solve, right, for the conformal symmetry, your exponents are all real. If you go to the Efimov case, then you have these complex solutions. So that already suggests that there is some way to transfer some concepts from one to the other. But of course, conformal symmetry itself will not be applicable.
I think we have one more question by Yama-san, and then the other one will take it in the discussion session.
So very interesting talk, and so the tetraneutron state. So that you are just talking about no peak according to your calculation. So you cannot have any peak for the tetraneutron state according to your calculation.
I cannot have any peak as long as the neutrons come from a point.
Okay.
So if I fold this with some initial distribution that, for example, comes from a helium-8 wave function, then there can be a peak.
Okay, so that means that, so that if you calculate helium-8, and so if you use a helium-8 wave function, maybe it might have some in peak.
Yes, so we played around with some things like that, and so if you have an extended source distribution, then you can have a peak.
Okay, I
so
see.
it's not, you don't have to do strange things to get a peak.
And the other one more question, and so according to your theory, what about the 6 neutron state?
So for the 6 neutron state, there will be a power law, and the energy distribution at low energies, so maybe up to 5 MeV or so, should grow like e to the power 6.2.
All right, thank you very much again. Let's thank him again. And so the next talk is by Liv Palmer,